All right, hello everyone, and welcome to the pre-lab video for this week's in-person lab, and that is in-person lab E12, the solutions of acids and bases, and the hydrolysis of salts. So before we get into the actual experiment itself here, I did want to point out that this week's pre-lab is pretty much a direct copy of last week's virtual pre-lab, in the sense that you are asked to calculate the pH of a strong base, you're asked to calculate the pH of a weak acid, and then the only thing that's really different is that you're going to use an ice table at the end of this one to determine the Ka instead. So the pre-lab here is relatively straightforward. I'm actually not going to talk a whole lot about it because I've got that video already in the can. Go to my YouTube channel. You will find the pre-lab video for V10, the pH and acid-base dilution lab. And I will talk about how you calculate the pH of a strong base, how you calculate the pH of a weak acid or a weak base using the Kb and ice table. And for number 4 here, you're going to use an ice table where you've got the acid in equilibrium with the hydrogen ion and the conjugate base ion. Both of those are aqueous as well. And so you would just set up your standard ice table. Where in this case we are starting with 1.20 molar of the HA, no hydronium, no A minus. And then we would know that we're going to lose some amount of the acid. We are going to gain some amount of the conjugates. My final concentrations are going to be 1.20 minus X, X, and X. And I should be able to use this pH value of 3.445 to determine the concentration of H+, which would give me the value of X, which I could then plug in to solve these E values and solve for the Ka. So not going to go too deep into any of that because, well, again, we already got the video out there. You should know how to do this already. The real purpose of this video is actually to talk about something that is going to come up during the procedure of this lab. So the first part here is all about pH probe and calibration. I'll talk to you more about that in the lab. Those of you that did the titration of the dissociation lab last week already have some familiarity with this. I'll talk to you all about it in some small part tomorrow or whenever I see you in lab. In part 2, you and a partner will be working together to measure the pH of strong acids and strong bases. One of you will take the acid, one of you will take the base. You'll share your data to get the other that you did not take. Same thing for procedure 3. One of you will take the strong acid or the weak acid, one of you will take the weak base. The weak base that we are using here is urea. the weak acid that we were using is acetic acid. And then what I really want to get into is part 4. In part 4, you're going to be measuring the pH of a variety of salt solutions. And the pH that we measure is largely based on conjugate behavior. And so when you get to not so much the data and results, because this is just all of your data tables, but more in this analysis part where you have to explain, okay, here are the 6 salt solutions in order of most acidic to least acidic. Here are the reactions that make it, okay, so why is this acidic? Well, it's acidic because of this. Why is this basic? Well, it's basic because of this conjugate's behavior. And that can be a little bit confusing. So I wanted to kind of get something out there that allows you to see just what it was that we were talking about and how to use that information. So the purpose of this video is mainly to talk about salt hydrolysis, because again, we've already talked about weak acid and weak base reactions, character, and all that from our lab last week, which again, if you read through the procedure, looks very, very similar to the simulation that you did, only you're going to do it for real this time. So salts. Salts do have acid and base characteristics because salts are usually the result of an acid-base reaction neutralization. Sodium chloride, for example, you can think of sodium chloride as being the product of hydrochloric acid reacting with sodium hydroxide. The hydroxide and the hydrogen ion annihilate each other, more or less. They neutralize each other and become water, and the leftovers are sodium and chloride, which if we take away all the water, the sodium chloride eventually becomes, well, solid sodium chloride. The question in front of us is how big of an impact on pH do those spectator ions ultimately have? And the answer to that goes into, well, how reactive are they toward water? So we know from experience that the stronger the acid is, the weaker its conjugate is, the weaker its conjugate base is. And the weaker the conjugate base is, the stronger the acid is, and so vice versa. So what we have to get into is just how strong are the acids and bases that these spectator ions come from. The stronger those acids are, the less of an effect they're going to have on water. In turn, and in some cases, they're not going to have any effect. So the criteria we use, if an ion is inert toward water, like sodium ion is, sodium ion comes from sodium hydroxide. Sodium hydroxide is a strong base. The strength of that base nullifies the acidic character of the conjugate sodium ion. So sodium ion does not react toward water, it is inert. And those kinds of ions do not impact pH. But if we do have conjugates that are derived from weak acid or weak base sources, then we know just based on things like titration curves, based upon conjugate acid-base behavior, that they are going to react with water. And when they react with water, they will either form hydroxide ions or hydronium ions. And the presence of those hydroxide ions will give it a basic pH, and the presence of those hydronium ions will give it an acidic pH. So again, it comes down to recognition. So let's take a look at each ion in turn. Most of the time, most of our ions that we're going to really be investigating are anions. And the reason for that is there are far more acids than there are bases. And so the acids all have the hydrogen ion as the acidic component, which means we are usually looking at basic character from the majority of our ions. And all anions are going to be evaluated for their basic behavior. Now that said, the inert ions are the ones that come from strong acids. So you list off your 7 strong acids, you're going to come up with hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, chloric acid, perchloric acid, and missing one here, sulfuric. And so if you look at those, these ions, their conjugates are going to be relatively inert, at least from a basic standpoint. So chloride ion, bromide ion, iodide ion, nitrate ion, chlorate ion, perchlorate ion. These ones are all essentially inert. We get a little bit of a pushback here with the sulfuric acid because the sulfuric acid does not create an inert substance. It creates an amphiprotic substance. The amphiprotic substance is the bisulfate ion, HSO4 -1. And to this end, it is inert as far as its basic character is concerned. However, it is not inert toward water completely because that extra H plus there, well, that guy is actually acidic. And if you look in your table of Ka values, you will find just how acidic the bisulfate ion is. Certainly not as acidic as sulfuric acid. Sulfuric acid is a strong acid. But the bisulfate ion is a weak acid that is still pretty robust in terms of its acidity. So if it comes from a strong acid, and you know your 7 strong acids, then we're going to either see inert character for all the ones that have no extra hydrogens, or we're going to see the acidic character coming from the other one. Basic anions, on the other hand, these are the ones that are conjugates of weak acids. And as a result, those weak acids are going to produce ions that are reactive toward water and form bases. So these are the 3 most common examples, but there are certainly others. So put any of those in here for X, and you would get a basic solution. So, sodium acetate acetic acid is a weak acid. And as a weak acid, the acetate ion is going to have basic properties toward water, meaning that it is going to act as a base toward water. And that means that the pH of a solution that contains acetates is usually going to be higher than 7. Same thing for fluorides, same thing for carbonates, same thing for oxides. We're going to see a lot of that kind of character developing in our anions. Cations we don't usually talk nearly as much about, because the majority of cations are in fact inert. Again, we can see this in their overall character. Look at the kinds of things that they come from. Lithium hydroxide, calcium hydroxide, sodium hydroxide, potassium hydroxide. All of these substances are strong bases, and that means that all of these ions themselves are inert toward water. The ones that aren't are your conjugate acids of weak bases. And so the most common of these examples, and again, this is why we don't see it as often, the most common of these is the ammonium ion. The ammonium ion being the conjugate acid when ammonia, NH3, dissolves in water. And that ammonium ion, because the ammonia is a weak base, has acidic character toward water and will cause water to accept this extra H plus and form an acidic solution. Now, the other place where we tend to see these are in your metallic hydroxides. So Metallic hydroxides, the ones that are not in group 1 or group 2, your irons, your transition metals, your coppers, your aluminums, these tend to be acidic kinds of ions as well. And if you've heard me talk at all about Lewis acid-base theory and the formation of complexes, we got into that just a little bit in that Le Chatelier lab. That acidic character comes out in those kinds of complexes and the ability to form complexes. But on the whole, again, we don't see these too often because most of the things that we encounter in the lab are alkali and alkaline earth metal salts. So again, usually we are looking on the basic side of the ledger, although occasionally we do see ourselves dipping onto the acid side. Now, just to get things a little bit muddy, there are those amphiprotic ions that are out there as well. Remember, these are the ones that they are the result of an acid-base reaction, and they have both acid and base capabilities. We already saw an example of one of those with the bisulfate ion, HSO4 minus. Now, we already rationalized that even though this is technically amphiprotic, it does technically have basic character. Its conjugate nature and the strength of that sulfuric acid make its basic character very close to 0. The acidic character kind of dominates the day. However, in the proper circumstances, if it were with a stronger acid, that stronger acid could force the bisulfate ion to act as a base and to take on an extra H+ ion. It would take some doing, but it is a possibility that that could happen. Others in this series, you've got things like sulfurous, bisulfate ion, HSO3 minus. You've got things like the bicarbonate ion, HCO3 -1. You've got your phosphate derivatives, the dihydrogen phosphate ion, and the monohydrogen phosphate ion that fall into this category as well. None of these are ever neutral toward water. The way that we evaluate their character primarily is based upon the comparisons of their Ka versus their Kb. So we look at the ion itself, we find it in our dissociation tables, and we say, okay, the Ka for bicarbonate is times 10 to the -12. And the Kb for bicarbonate is 10 to the -5th. Well, the Kb is the one that's the better one. Bicarbonate usually acts as a base, and that is actually true. Bicarbonate ions usually are basic in water rather than acidic. But we always look to that comparison. And again, that's how we end up at the correct conclusion about the bisulfate ion, because the Ka for bisulfate is pretty good. I don't know the number off the top of my head exactly, but it's relatively robust. Whereas the Kb value for it is close to 0. It's very, very non-basic. But now that we know this, it allows us to take into consideration, when I look at the formula for a salt, I can see that that salt is going to fall into one of these 4 categories. And based upon which category it falls into, I'm going to be able to evaluate whether it's acidic or basic or neutral. So scenario number 1, the easiest scenario. I've got a cation and an anion, and they are both inert toward water. So sodium chloride being kind of the prime example of this. Sodium came from the sodium hydroxide, which is strong. Chloride came from the hydrochloric acid, which is also strong. So neither of them have anything to say to water. They're going to be completely neutral toward water. Number 2, this is our most common scenario for non-neutrality. We have a cation that is inert, usually a group 1 or group 2 metal ion, but an anion that is derived clearly from a weak acid. And as a result, we're going to have a basic pH for this. The flip argument is true as well. Scenario 3, if the anion were inert but the cation were not, well, we just flip the script. The salt's going to be acidic as a result. Now, if they're both reactive toward water, this is the least common scenario. What we have to do is we have to compare the relative Ka and the Kb. Whichever one is bigger is going to dominate and affect the pH the most. Again, this is kind of the most rare of the situations. This is where we get into stuff like ammonium acetate or iron 3 phosphate, where in some of those cases, heck, the salt's not terribly soluble in the first place. And even if it is, we still need to evaluate the Ka versus the Kb characteristics. Now, the easiest way to think of it is just using simple greater than and less than logic. When I'm evaluating where these come from, I'm going to evaluate the acid versus the base. Whichever one is stronger is going to dictate the pH of that solution. So if I have a strong acid and a strong base, I can see that they are equal to each other here. Then I would expect a neutral pH. And that neutral pH should be somewhere around 7. Now in the laboratory, getting pH 7 solutions is actually a lot more difficult than you think because, well, we're in an open atmosphere most of the time. Carbon dioxide finds its way in. Carbon dioxide is going to lower the pH down into, the middle 5s and 6s, if depending upon how much actually ends up getting dissolved. So in the laboratory, that is really difficult to see. But it is still, that's where it should be, provided that we are able to degas as much of that water as possible. In the scenario where we have a strong acid versus a weak base, we can see that the strong is better than the weak. We get an acidic solution. Our pH is going to be less than 7 as a result. When our derivatives are from a weak acid and a strong base wins. We get a solution that is basic and a pH that is going to be greater than 7. When both are weak, there is no definitive comparison that we can make just by looking at the chemical formula. I have to go to the table of Kas. And so I compare the Ka and the Kb, and depending upon which one is best, I'm going to evaluate whether it's either going to be neutral, acidic, or basic. So let's take a look at an example problem. Now, the way to do these example problems is we are going to cut the compound in half. And on each side, we are going to evaluate where that ion came from and if it is strong or weak. So, for example, calcium chloride. Calcium comes from calcium hydroxide. Calcium hydroxide is a strong base. Chloride. Chloride comes from hydrochloric acid. Hydrochloric acid is a strong acid. I can see from this evaluation the two are equal to each other. We expect this to be neutral. In the second example here, again, split it right down the middle. I've got sodium Sodium is derived from sodium hydroxide. Sodium hydroxide is a strong base. I've got carbonate ion. Carbonate ion is derived from its conjugate acid, which is the bicarbonate ion, HCO3 minus. Now, we know that carbonic acid, H2CO3, is a weak acid, which means that bicarbonate ion has to be a weaker acid than that. So this is a weak acid. I can see that my strong base is better than my weak acid. So this is going to be a basic salt. In aluminum nitrate, again, start by splitting it down the middle. I've got aluminum. Aluminum is derived from aluminum hydroxide. Aluminum hydroxide is no one's definition of a strong base. This is weak. Nitrate is derived from nitric acid. Nitric acid is, of course, a strong acid. I can see that the strong acid is greater than the weak base. This is going to be acidic. In the last one, I've got zinc and iodate ion. Zinc would be derived from zinc hydroxide, which again is a weak base. Iodate would be derived from hydroiodic acid, iodic acid, which is also weak. So since I don't have a definitive answer here, I've got to go to the tape. And by the tape, I mean I've got to go to a table of values that give me Ka or Kb values for these particular acids so that I can compare them. Now, there are a variety of different places that you can get these values. Our book has some of them. The appendix tables have a number of them as well. So I'm going to go there first and foremost. So I need zinc, and not the zinc ion. I'm actually going to be looking for zinc hydroxide here. Went past it. Zinc hydroxide has a Kb of 7.94 times 10 to the negative 7th. By comparison, iodic acid has a Ka of 1.7 times 10 to the negative 1st. So going back, we have on the zinc hydroxide side, (7.94 times 10 to the negative 7th, which is not that great. And on the iodic acid side, we have 1.7 times 10 to the negative 1st. So it is pretty easy to see that the acid side here is in fact better than the basic side. And so as a result, this is going to be an acidic salt. And so that's all that you need to do. And so in terms of what does that actually mean toward those questions? Well, the question we would want to know is, in the case of some of these, why is it that the sodium carbonate gives off a basic vibe? What we would do is we would say, okay, well, a carbonate ion reacts with water to make bicarbonate ion. And hydroxide ion. So this ion generates hydroxide, and that's what brings the pH up. So this concludes our little walkthrough of the concept of salt hydrolysis, and that should help you with doing that last part of the lab. Again, for the pre-lab that is due tonight, it's not as big of a deal because, again, that's not one of the questions in the pre-lab. But if you have questions about that pre-lab, I certainly would defer you back to that V10 pre-lab video that I recorded last week. Until that point, I will see you in lab. Have a good afternoon.